So with a geometric probability, we're going to find a lot of similarities between geometric calculations and binomial calculations. And we started with binomials by saying that we need to satisfy 4 conditions. We need a success or failure. We need a set number of observations. We need independence between all of our observations. And lastly, we need a set probability of success for each of our observations. Now, when we were analyzing different scenarios and trying to determine, does this satisfy the binomial model, you may recall that one of the questions that we had was kind of a bizarre question. It was like, there is a couple that they intend to keep having children until they have a boy, or something to that effect. Maybe it was girl, I can't remember. But that did not fit our binomial model because there was no set number of observations. Instead, you're going to keep trying until you have that success. That is a geometric probability, where you keep going until you get that first success. And we're going to see some scenarios that are less strange than the one that we just discussed, but where this geometric model really does make sense, okay? Where you want to keep going until you get a successful outcome. Now, we will look at the calculator, we will look at GeoGebra, but you'll find that the equation is actually pretty straightforward and easy to use for geometric probabilities. And so we have that right here at the top of our notes. It says that if we have a p probability of success and complementary probability 1 minus p as a probability of failure, the probability that the first success occurs on the nth trial is given by this equation. Probability of failure raised to the number of failures times probability of success. This is our counting principle in action, where if you are flipping a coin 4 times, or you want your first success, your first head occurs on your 4th flip, that means you have 3 failures ahead of that. N is when that success occurs, so n minus 1 gives you the number of failures you have before you get that success. So this is literally just failure times failure times failure times success. So we have a table here for a problem that says you roll 2 dice and add them together. Now that sample space that we've seen before, 36 possible outcomes. We want to find the probability that we will roll a 7 on the first trial, the second trial, the third, the fourth, and so forth. Now, if you recall, on that chart, a sum of 7 was the most common outcome. It was along that main diagonal. It was 6 of the 36 possibilities. So we are going to say that P is equal to 1/6. Our probability of failure, 1 minus P, is 5/6. So as we start to make this chart, I'm going to put this as decimals. 1/6 as a decimal is 0.16 repeating. And then to get this value, that would mean that we failed the first time. So we got something other than a sum of 7 for our first roll. So that means that we had a failure occur, and then we had a success. So you could multiply this out by hand a little bit if you want. 5/36, or as a decimal, we're looking at 0.138, and the 8 repeats. Now let's continue on. For this event right here, now our first success occurs on our third roll. So to get to that point, we had 2 failures. So 5/6 squared times 1/6, or just multiply our previous answer by another 5/6, right? Because multiplication is commutative. So multiply that by 5/6. We're now down to 0.1157, approximately. Look what's happening with these probabilities. 16%, 13.8%, 11.5%. They're going down. And that makes sense. They're going to continue to go down. And this can go on infinitely, right? You could roll the dice 100 times and still never have a sum of 7 occur. It's very unlikely, but it could happen. Maybe the 100th roll is that first time that you roll a sum of 7. Every time you're adding more detail to what goes into that outcome, you're lowering that probability. Okay. So, this is pretty straightforward in terms of how you would use this equation to make these calculations by hand. But if you wanted to, you can use the calculator to do that as well. Okay? It's called a geometric PDF. So let me flip screens and get that going for us. All right, so on the calculator, same menu as before, second distribution, and we jumped directly to the bottom. You see the binomial PDF and CDF as letters A and B right there? Well, now we want our last 2 entries, geometric PDF and CDF, when we're interested in when that first success occurs. So, letter E, geometric PDF, this would give us one of those columns on the chart that we were just making. So we left off by looking at the probability that our first success, the first time we roll a 7, will be on our 4th attempt. So we only have 2 entries here. P, probability of success, which we said was 1/6, and the X value is when we want that success to occur. We want it to be on our 4th roll. Paste that in. There's our answer. About a 9.6% chance of that happening. Continuing to go down from our 11% chance that we had before. Okay. Now, the other option that we have is geometric CDF. Remember, the C stands for cumulative density function. So if we were to alter our interpretation and say, what's the probability that our first success will occur by our 4th roll? Meaning that we got a sum of 7 on our 1st, our 2nd, our 3rd, or our 4th. What's happening is we're adding all of these probabilities together. So same kind of thing. P was 1/6. I'm going to put 4 for our X value, meaning that our first success occurs by our 4th roll. Hit enter. Now, about a 51.77% chance, a much higher probability now. Because you're not just saying that it's occurring on the 4th attempt, it's occurring by the 4th attempt. Right? And we've added all of those together to get to that point. Any questions so far? Let me flip screens back here. we had said that this probability here was about 9% or 9.6. If I were to add those, and there's going to be a rounding discrepancy here, but let me just get a rough idea. 0.16 plus 0.13 plus 0.1157 plus 0.096. Yeah, just by adding these, I'm at 0.5097. Pretty much that same 51% that I got by doing the geometric CDF, the cumulative probability there. And if we were to take this out for a further 5 rolls, this number would continue to go down, while that geometric CDF number would continue to go up a little bit. Questions here? We have another problem here. It says, it is estimated that 45% of people in fast food restaurants order a diet drink with their lunch. Find the probability that the 4th person orders a diet drink. Okay, you're interested in that 4th customer. Okay? And let's be a little bit more explicit here that that 4th customer is going to be the first diet drinker of the day. Okay? That's what we need for geometric. So, we could do geometric PDF, or 45% success. That means 55% failure for our first diet drinker of the day to be on our 4th customer. That means that we have 3 failures in a row. So 0.55 to the 3rd power times that probability of success, 0.45, left my calculator over here, 0.55 cubed times 0.45, we're looking at about 7.5% chance that that first diet drinker of the day will be the 4th customer. Now the second part says also find the probability that the first diet drinker of the day occurs before the 5th person. Like we saw with the binomial problems, you need to pay close attention to the wording. Okay? That's the difference between like a less than sign versus a less than or equal to sign. So if we're saying that this first diet drinker occurs before the 5th person, it could be the 1st customer, it could be the 2nd, it could be the 3rd, it could be the 4th. But do not include that 5th. We have a cumulative probability here. So we're going to do a geometric CDF, probability of success, 0.45, and have it add up through that 4th customer. So I'm just going to write this out here. Oh. We have it right here. And we get our probability of about 0.908, almost 91% chance when you're adding all of those together. Now, I also want to show you GeoGebra. And I will admit that as easy as GeoGebra was for binomial problems, and I was really kind of pushing that last week for you, for geometric, it is not as nice. In fact, I would probably recommend the calculator, or in these cases, just doing it by hand for some of these problems. But I do want to show you GeoGebra real quickly. All right? So with GeoGebra, flip screens. Of course, it kicked me out. with GeoGebra. So we saw this starting with a binomial. We have this drop-down menu that it starts with a normal curve. That's the default setting. We were able to change that to binomial. Well, you can't see it when I click it on here for some reason, but there is no geometric distribution that comes up. There is a hypergeometric, but that's not what we want. Okay? Instead, the option just below binomial is for a Pascal distribution. Now, geometric is a special case of this Pascal distribution. We're probably not going to look at this in other cases later on this year, but a Pascal distribution looks at multiple successes occurring throughout the distribution. So to make this work for geometric for us, we can select Pascal, but we need to have that n value as 1. We only want one success. We are interested in when that first success occurs. Let me change this probability so that it models this fast food problem that we just talked about. So I'm going to change that p-value to 0.45, and just like we saw with binomial, we have this probability distribution on the right side. Now you'll notice that these numbers here are different than when we did it with the graphing calculator. Everything is shifted by 1. Okay? K as 0 means that we have our first success occurring on our first attempt. You can think of these numbers as representing the number of failures that you have. So when you have 0 failures, your first attempt is successful. And that probability of success was 0.45. We change this to 0, 0. Okay, so we just have that first column highlighted. There's that 45% success. And we could go down 1, 2, 3. We had seen a probability of 3 failures. Probability of 3 failures was about 7.5%. That means 3 failures, and then on that 4th attempt, we have our first success. Okay? So you can use this. You can make a cumulative probability. Like if I want to know the probability of getting that first success by my 4th attempt, that means I could have 0, 1, 2, or 3 failures. Same kind of thing, 0.9085 is that probability, that cumulative probability that we saw. You also have an option here of clicking this button next to Pascal, and it turns this into a cumulative distribution, okay, where you can see this as a step function, how those probabilities add up, and it shifts the distribution chart as well, showing you that we're getting really, really close to 1 as we increase these number of outcomes. Okay. Another word of caution about using GeoGebra, these numbers down here, mean and standard deviation, they are not the mean and standard deviation that we need for a geometric distribution. Okay? We have this slightly different interpretation which affects those numbers. So it's kind of a good news, bad news scenario. Bad news is these are not the numbers that we need. Good news is the mean that we are finding is really easy to find with the equation. And so let me shift back over there unless anybody have any questions about using GeoGebra. All right. Flipping back. So the mean for a geometric distribution is found by this equation right here. Just 1 over p. where P is that probability of success. Now, we've also referred to mean as expected value. This is when you would expect that first success to occur. It's the average. So with our fast food example, we had a p-value of 0.45. So the mean in that case, 1 over 0.45, divide that out. 2.2 repeating. So we would expect our first diet purchase of the day to be on about our second customer, second or third customer. Okay? It is an average. We also have an additional equation right here that says the probability that it takes more than n trials to see the first success is given by this equation, probability of failure raised to the nth power. Think about what that means. The probability it takes more than n trials to see that first success. We're not saying that our first success occurs on the 8th or 9th or 10th trial. We're just saying that we have 7 trials in a row where we were unsuccessful. Probability of failure raised to the 7th power, the number of failures in a row. This is just calculating the likelihood or the probability of getting that many failures in a row. I think this example down here will help illustrate that. Written before the days of ride-sharing companies, this one says, in New York City at rush hour, the chance that a taxi cab passes someone and is available is 15%. How many cabs can you expect to pass you for you to find that one is free? Well, how many can you expect to pass by? This is an expected value. This is a mean. So expected value is the mean, is 1 over p. So our probability of success, the cab is available, is 15%. So just simply 1 over 0.15, 6.6 repeating. So we would expect around the 6th or the 7th cab to be our first success. And you can see how this geometric model is perfect for analyzing this situation. We don't need 10 open cabs coming. We just need that first one to be a success for us, and then we're good. Okay? That's what this geometric model does. Part B of this question, what is the probability that more than 10 cabs pass before you find one that is free? Again, we don't care if the cab that's open is the 11th one or the 12th or the 100th cab to come by. This question is just saying, what is the probability that more than 10 cabs will pass before we get that first one that's free? It could be the 11th, it could be the 12th, but we want 10 failures in a row. 1 minus p, in this case, 1 minus 0.15 gives us 0.85 raised to the 10th power. 0.85 raised to the 10th, 0.1969. Almost a 20% chance that there will be 10 cabs in a row that go by that are all occupied. Any questions here? All right. On our next page, we have one more practice problem. It says, a well-traveled highway has its traffic lights green for 82% of the time. If a person traveling the road goes through 8 traffic intersections, complete this chart to find the probability that the first red light will occur on the nth traffic light, and B, the cumulative probability that the person will hit the red light on or before the nth traffic light. Okay. First off, let's not make this worse than it really is. We have an 82% probability of a green light. However, a success in this problem is going to be when we encounter our first red light. So P, the red light, is going to be an 18% probability. The failure is a green light. That's the 82% probability. Make sure that you are clearly defining that in the terms of the problem. Continuing on here, we're not going to write out this full chart, but I want you to see how these probabilities fit together. Okay? So, we're driving along the very first intersection that we get to. There's an 18% chance of it being red. There's that probability that our first intersection is a success. And the cumulative probability, also 18%. We haven't had any other opportunities yet, so just 18. Now, number two, we could do geometric PDF to get this row. Okay? This would be PDF. This would be CDF. Or, the equation's not that bad. That would mean that we'd have a failure, a green light, on our first intersection, and then we have a success, a red light. So we multiply those two. 0.82 times 0.18. We have 1476. Okay. 0.1476 is that probability that that second intersection will be our first red light. The cumulative probability would mean that either the first one or the second, this, or means add. We're adding these two numbers together. Okay, so 0.1476 plus the 0.18, we are at 0.3276. Almost a 33% chance that we'll have our first red light on one of the first two intersections. And we could keep going. Okay? We would then have two green lights, then a red light for that third slot. Okay, so we can really just multiply this number, 0.82 squared times 0.18, 0.121, and add that to our previous value. And you can see this is going up. The cumulative probabilities are going up as this is going down. Let's jump to this last one right here. If we were to say that cumulative probability that our first red light will occur by our 8th intersection, that's a geometric CDF. I'm just going to do it on my calculator right here. 0.18, and the x value is 8. This number right here would be 0.7956. Almost an 80% chance that we will have a red light by that 8th intersection. Okay. You can see this number in this middle row is approaching 0. Okay. 18, 14, 12%. While this number, these cumulative probabilities, okay, by the time you get to the 8th intersection, or the 18th, or the 100th intersection, it's almost guaranteed that you will have a red light by then. These probabilities are approaching 1. Okay. Still going back to that success or failure of the binomial traits. Down here, also find the expected number of traffic lights to hit a red light and the probability you will go through more than 8 lights before seeing your first red light. Well, expected number, that's expected value, or mean. So in this case, 1 over that probability of a red light, 0.18. 1 divided by 0.18. We're looking at 5.5 repeating. So we would expect that first red light to occur around our 5th or 6th intersection. The second half of this question, the probability you will go through more than 8 lights before seeing your first red light. Well, this uses that equation that we talked about. That means we have 8 failures in a row. We don't care if the first red light's on the 9th, the 10th, the 76th intersection. We just want 8 failures in a row. So that would be the probability of a green light, 0.82 to the 8th power. .2044. What's the relationship between this number and this number? How are those two numbers related? Pretty much 80%, pretty much 20%. They're complements of each other. They add up to give you 100%, 1. Okay? Now that should make sense because this is the cumulative probability. This is the probability that your first success will occur by the 8th intersection, on the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, or 8th. This number represents 8 failures in a row, and that first success occurs somewhere beyond the 9th, 10th, 11th, all the way up through infinity. So you could look at this as the inversion of this geometric CDF. You could calculate this same number by doing 1 minus geometric CDF of those same values, the 0.18 and the 8. 2 different ways to get that answer. But hopefully, looking at both helps you understand what they're calculating. All right. That's it in terms of new stuff for today. Any questions about what we just talked about? Geometrics, very similar to binomial. Okay, 3 of those 4 conditions are still the same. We still have success or failure. We still have independence. We still have a set probability. It's just we don't have a predetermined number of observations. And instead, we're going to keep going until we get that first success. Our third page, I have 2 additional practice problems here, kind of similar to this red light, green light intersection one. This one says a basketball player hits 76% of his free throws. He shoots until he misses. Okay? That miss is going to be the success. So we need to complete the chart and find the probability and the cumulative probability of when that first miss will occur. And then expected number and probability of missing 10 in a row. Or I'm sorry, making 10 in a row before that first miss. Yeah? Don't worry about these histograms. You don't need to draw those. In fact, in the previous problem, I was just writing over them. Yeah? And then we have another question down here talking about winters in Buffalo, New York. Probability of snow on any given January day is 15%. we want to complete this chart. Will that first January snow occur on New Year's Day, January 2nd, 3rd, 4th, 5th, 6th, 7th, and so forth? Okay. Same type of setup, expected value, and then what's the probability it will go a week without seeing snow? You do not have any graded homework assignments, okay? Nothing that you must submit this week. Okay? However, I will say you certainly need to be practicing and familiarizing yourself with these types of problems in preparation for our quiz on Thursday. So you have these two problems to take a look at and practice. Back on Canvas, I have two additional documents. And one is called this Random Variable Binomial Geometric Practice. And looks like this. Remember, we talked about random variables right before winter break. Okay, so I know that that might have been lost in the shuffle here, but random variables, they're numeric representations of outcomes. So we have a scenario provided here and the probability distribution given to us. An ice cream shop, this represents the number of scoops of ice cream that people will purchase. So you can get 1, 2, 3, 4, or 5 scoops with your purchase, and the probabilities of their customers buying those things. You can see, pretty small, 3% chance that a customer gets 5 scoops of ice cream. So you're using this to calculate some probabilities. Probability X is less than or equal to 2, meaning that a customer gets 2 or fewer scoops. You can add those together. Number 3 asked for the mean of this distribution. Well, mean is expected value, and expected value, when you're provided with the entire probability distribution, you're taking the random variable and multiplying it by its probability, adding it to the next random variable, multiplying by its probability, plus this times this, plus this times this, plus this times this, all the way down. Okay? Here's the equation. Okay? A1 times probability of 1 plus A2 times probability 2, all the way down. Okay? You're adding those all up, and giving you all of those random variables times their probabilities. Okay. I've crossed out several things here that you don't need to worry about. All right. In addition, number 6, which I hadn't originally crossed out, but it's there. And then we have some binomial and geometric problems intermingled as well. According to recent statistics, 22.8% of people in the United States are vegetarians. We take a sample of 18 people randomly. What's the probability that whatever? Yeah. So we have our probability. It is binomial. So you're using that to calculate. We have a mean and a standard deviation down here as well. Last page, we have a geometric problem. You can kind of read through that. Some practice for you right there. And then additionally on Canvas, I have our review outline. Your quiz format. It is a Canvas quiz. You're looking at, it's either 30 or 35 points. I'm undecided on if I want to include this one problem on there. So I'll let you know officially on Wednesday. But you'll have a handful of multiple choice questions. Most of the problems are going to be open numeric response problems where you type in the decimal entry. Yeah? I strongly recommend that you are familiar with GeoGebra or the graphing calculator or both. Okay? Been working a lot with those the last couple weeks. Make sure that you're well versed in at least one of those. And because it is an open note quiz, I mean, here's an outline that covers pretty much everything that we've talked about. And you might want to have this handy to serve as a reference sheet. Okay, some rules of probability I have there. Expected value for a random variable that I just discussed. Probability distributions. Here are those conditions for a binomial model. Success or failure, set number of observations, independence, and fixed probability. Here's the equation for a binomial calculation, which you probably do not want to do. Use either the calculator or GeoGebra. I do show you the commands for the calculator combination, or for the calculator binomial calculations. If you are using the calculator for binomial, make sure that you know the difference between binomial CDF and 1 minus binomial CDF. And we know that the calculator starts adding with 0 and goes through where you tell it to stop. Mean of a binomial is n times p. Standard deviation of a binomial, I wrote in there, square root of n times p times the probability of failure. And then what we talked about today, geometric. The only difference is you're interested in when that first success occurs. Here's the equation. Here are the commands for the calculator. Expected value or mean is 1 over p. And the probability that it takes more than n trials to see that first success. Failure raised to the number of trials, or we just saw at the very end, 1 minus geometric CDF. I then have 3 pages of practice problems. And the first one, I just give you several different cases where you need to determine, is this a binomial model, is it a geometric model, or is it neither? Okay. So read through, have those conditions available to you, and determine what makes sense in that scenario. A couple questions down here is probability distribution that you're using to answer that. We have a chart set up according to a 2005 Gallup poll. About 30% of Americans own at least one gun. A sample of 5 people is chosen at random. Make the probability distribution. Now, you could do this with GeoGebra. Okay? We saw that that's provided for you on the right side. You could do this with the calculator. Binomial PDF, where the n value is 5, taking a sample of 5 people. Probability of success is 0.3. And do not give it an x value. Just hit enter, and it will give you all of these probabilities in order. You just read them off, copy them down. And once you have that distribution created, answering these questions is pretty straightforward. You could use that, or you could use the PDF, CDF stuff. This next question, now we have a much larger sample of 25 people. You're no longer making the chart, going straight to either PDF or CDF or GeoGebra to calculate those. And then the last one, we have an example. According to a 2019 survey, only 4% of customers prefer to use or purchase gasoline using cash. What is the probability that 6 consecutive non-cash purchases will go by before a cash purchase on the 7th? Sounds geometric to me. Okay. So, working towards that quiz on Thursday. Next time I see you on Wednesday, I'll have these keys available for us. As you're working through, if you come across any questions, either make note to ask me about that on Wednesday or come see me in academic resource time. Okay? You need to practice doing these things. This is not the type of thing where you can just look at it or look at my key and say, yeah, I know how to do that. Can do it, can do it. No, you need to try these. Okay? Practice doing it. That's how you get better with it. I will say that for our quiz on Thursday, I will not be here. I have a remote conference that I'm attending. So there will be a sub here, but everything will be set up in Canvas, ready to go. I am setting the time for the entire class period for that quiz. So hopefully there won't be any issues that either the sub has to remedy or myself. I'm going to try to reach out to the sub in advance to just make sure that that person knows that there will be a quiz on that day, but everything should be, knock on wood, should be self-operating. Okay. All right. With these remaining 15 minutes or so, I'd like you to start practicing with either this review or those geometric problems that we had just discussed. Okay. And please ask me if you have any questions. Okay. Any questions right now? Right. Very good. So go ahead, get started. I'll be here.